Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation.
The paper titled, "From Words to Numbers, Your Large Language Model is Secretly a Capable Regressor When Given In-Context Examples," investigates the capability of pre-trained large language models, LLMs, to perform linear and non-linear regression tasks without additional training or gradient updates, solely through in-context learning. The methods proposed and the experimental setup are detailed as follows. In-context learning for regression. The core methodological innovation explored in the paper is the application of in-context learning, ICL, to regression tasks. In-context learning involves providing a model with a few examples of a task within the prompt and then asking it to perform the same task on a new example. This approach leverages the model's ability to generalize from the examples provided to it directly in the prompt, without any explicit retraining or fine-tuning. Datasets. The paper utilizes both synthetic and real-world datasets to evaluate the regression capabilities of LLMs. These datasets include linear regression datasets, tasks with a direct linear relationship between inputs and outputs. Non-linear regression datasets, including the Friedman datasets, which are standard benchmarks for evaluating regression models. Regression with non-numerical inputs, a novel task designed to assess the model's ability to handle abstract regression tasks where inputs are symbolic rather than numeric. Models evaluated. The study evaluates a range of LLMs, including GPT-4, Claude 3, and Llama 2, among others. It also compares their performance against traditional supervised learning methods like random forest, gradient boosting, and linear regression models, as well as heuristic-based unsupervised models. Experimental setup. In context examples, the LLMs are provided with a set of input-output pairs directly in the prompt as examples of the regression task. Performance evaluation. The models are then asked to predict the output for a new input based on the examples provided. The performance is measured using metrics like mean absolute error, MAE. Scaling with context size. The paper investigates how the performance of LLM scales with the number of in-context examples provided. Analysis of regret. The paper introduces an analysis of how the cumulative regret, i.e., the cumulative difference between the model's predictions and the optimal predictions, evolves as more in-context examples are provided. This analysis helps in understanding the learning dynamics of LLMs in the context of regression tasks. Empirical and theoretical insights. The study provides both empirical results demonstrating the regression capabilities of LLMs and theoretical insights into why and how these models might be learning and generalizing regression tasks from in-context examples. The methods proposed in the paper highlight a novel application of in-context learning, demonstrating that pre-trained LLMs can effectively perform regression tasks, rivaling traditional supervised methods, without any additional training. This opens up new avenues for utilizing LLMs in tasks traditionally reserved for specialized regression models.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled, "Patchscopes, a Unifying Framework for Inspecting Hidden Representations of Language Models," introduces a novel framework known as Patchscopes for inspecting the hidden representations of large language models, LLMs. The methods used in the paper are as follows. Patchscopes framework. The Patchscopes framework is a modular system that can be configured to extract various types of information from LLM representations. It operates by patching a representation into a separate inference pass. This process encourages the extraction of specific information independently of the original context. Interpretability methods. The authors demonstrate that many existing interpretability methods can be cast as instances of Patchscopes. These methods include those that rely on vocabulary projections and computation interventions. The authors of the paper conducted a series of experiments to validate the effectiveness of the Patchscopes framework. The experiments were designed to test various aspects of the framework, including its ability to decode next token predictions, extract specific attributes, analyze entity resolution in early layers, improve expressiveness from cross-model patching, and its application in self-correction in multi-hop reasoning. Decoding of next token predictions. The authors compared the performance of Patchscopes with existing methods like logit lens and tuned lens in estimating the model's next token prediction from its intermediate representations. They used multiple large language models, LLMs, for this experiment. The results showed that Patchscopes consistently outperformed the other methods, especially in the later layers of the models. Extraction of specific attributes. In this experiment, the authors used Patchscopes to extract specific attributes from the hidden representations of LLMs. They compared the performance of Patchscopes with linear probing, a common method for checking if certain attributes are encoded in hidden representations. The results showed that the Patchscopes method significantly outperformed probing in 6 out of 12 common sense and factual reasoning tasks, and worked comparably well to all but one of the remaining 6. Analyzing entity resolution in early layers. The authors used Patchscopes to study how LLMs contextualize input entity names across multiple layers. They crafted a target prompt for generating a description of a given subject and applied it to the hidden representation at the last subject position in the source prompt across the early layers. The results showed that Patchscopes can effectively verbalize the gradual entity resolution process. Expressiveness from cross-model patching. The authors demonstrated that when patching representations across different sizes of the same model, e.g., from a smaller to a larger model, the expressiveness of the inspection can be improved. They conducted experiments on next token prediction and entity resolution, and found that using a larger model for inspection can enhance the output expressivity. Application: self-correction in multi-hop reasoning. The authors demonstrated the practical utility of Patchscopes in a multi-hop reasoning task. They showed that Patchscopes can be used to correct latent multi-hop reasoning errors, improving the accuracy from a baseline of 19.57% to 50%. In conclusion, these experiments demonstrate the effectiveness and versatility of the Patchscopes framework in inspecting and interpreting the hidden representations of LLMs.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled SOAR: Improved Indexing for Approximate Nearest Neighbor Search introduces a novel data indexing technique called SOAR, spilling with orthogonality amplified residuals, for approximate nearest neighbor (ANN) search. The methods used in this technique are as follows. Spilled VQ assignment. SOAR assigns each data point to a second VQ partition, resulting in a second partitioning residual that forms an angle with the query. This gives the ANN algorithm a second chance to find the nearest neighbor. This approach can be extended to further assignments as well. Spilling with orthogonality amplified residuals, SOAR. SOAR uses a novel loss function to assign a data point to multiple VQ partitions. The loss function is designed to minimize the quantized score error specifically when the original assignment has a high cosine of the angle between the query and the partitioning residual. This is achieved by adding a weighting term for the cosine of this angle in the loss function. Implementation considerations. SOAR comes with some memory overhead due to its multiple assignments causing some duplication of data. However, the overhead is quite negligible because only the product quantized, PQ, data point representation is duplicated. SOAR also results in a small amount of query time CPU overhead over a non-spilled VQ index, due to SOAR's need for deduplication. Spilling to further centroids. The analysis conducted in the paper focused specifically on the case of assigning to 2 partitions. This can be generalized to an arbitrary number of further assignments, where each subsequent assignment is done with a loss considering the distribution of quantized score errors from all prior assignments. Related works. The paper also discusses related works such as spill trees and graph-based algorithms, and how SOAR differs and improves upon these methods. The experimental work conducted to validate the methods involved several steps. K-means recall, KMR, curve comparison. The effectiveness of the spilling with orthogonality amplified residuals, SOAR, method was first evaluated using KMR curves. These curves were plotted for various datasets, including GLOVE 1M, Microsoft Spacev, and Microsoft Turing ANNS. The The results showed that SOAR improved the KMR performance, especially for larger datasets and higher recall targets. Correlation analysis. The researchers conducted a correlation analysis to understand how SOAR improves the KMR and overall vector quantization (VQ) index quality. They found that SOAR significantly reduces the correlation between the cosines of the two angles, thus increasing the efficacy of multiple VQ assignments. Effects of dataset size and recall target. The researchers investigated how the benefits of SOAR change with the size of the dataset and the recall target. They found that the benefits of SOAR increase as the dataset size and the recall target increase. End-to-end recall speed benchmarks. Finally, the researchers compared the performance of SOAR with state-of-the-art algorithms in two standardized benchmarking frameworks. They found that SOAR improved upon the performance of the existing algorithms. Memory consumption. The researchers also measured the memory consumption of the ANN indices in these benchmarks. They found that the increase in memory usage due to SOAR was minor. Overall, the experimental work demonstrated that SOAR significantly improves the performance of VQ indices for approximate nearest neighbor (ANN) search.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.